So, welcome everyone. My name is Tobias Ternström, and I'm a program manager in the SQL product group. Everyone does know this is about SQL, these square, columns, rows, relational databases. Good, good. So the session, if you read the description, it's not entirely good title. It's more like Azure SQL database all over the hood. So someone else named it. There we go. So we'll try to cover a bunch of stuff over this next hour. First, just kind of set the stage about SQL. So we have kind of 3 different ways to run SQL, and just very briefly how you should think about each of these. We'll talk somewhat about business continuity. So we made some announcements, or Scott made some announcements on the second day keynote. We'll talk about development best practices, and we'll finish off with talking a bit about partitioning across databases or charting. But starting off with these 3 different ways to run SQL. So if you look at this kind of chart here, we have a continuum of basically 3 ways to run the product. You have SQL Server that you run on the raw iron, right, directly on the machine. You have SQL Server that you run in a VM, and you have Azure SQL database that you run somehow in the cloud, right? And it's worth noting that these are somewhat different products. So they're useful and good for different things. So if you look at the first one, SQL Server on the raw iron, what you have there is obviously full compatibility with SQL Server, since it is SQL Server. And you have the ability to scale up to some huge machines, right? You can buy a bigger machine, buy a bigger machine, buy a bigger machine. And this shouldn't be discarded, right? You have lots and lots of applications, typically these big monolithic things that basically require a lot of hardware. And it's kind of cost prohibitive to go and just re-architect the app or redesign the app to run on something else. So some applications, typically older applications, just require a lot of hardware power, and then the right thing is to run them on SQL Server directly on the physical hardware, right? Then you have SQL Server in a VM, which you can obviously run up in Azure, and this, the big deal here is you can't go as high up in hardware performance as you could on your own enterprise-grade hardware, just because we standardize the hardware we buy in Azure, right? So there is a limit to how big of a single virtual machine you could actually buy. Now, provided that your app actually fits within this VM, what you have here is full compatibility with SQL Server. So if you run an app and the performance-wise it fits in a VM, you don't have to change the app in order to make it run in a VM, right? So it's exactly the same, fully compatible. And then you have Azure SQL DB, which is different product. And we went through a lot of churn on the design here years back, where we thought about what do we want to deliver. And the main thing in Azure SQL DB is that it's very focused on developers, right? So making you productive developing your apps. So it automates a huge amount of these management tasks that you would have to deal with were you running on SQL Server or some other RDBMS on physical machines or even on VMs. So what we did here is we decided that what we want to virtualize is a database, not an instance or a machine, right? And this is somewhat interesting. So because of the fact that we do this, it gives us a lot of latitude to basically optimize the system that we run in and provide you very, very interesting high-level services. So things like HA is completely built in. You never, ever see it. But it also gives us a different instruction set, since you have to be within a database. So you have tables, stored procedures, triggers, views, all of this good stuff. But you don't have, for example, SQL Server agent, or you don't have right now at least, cross-database queries, because the container now is the database. We have the concept of a server, but we call it a logical server, and it's really just a list of your databases. So let me just show you to kind of set the stage. How many of you guys use SQLDB today? No one? Oh, for you in the front, so most people raise their hands, so that's good. But anyway, the main thing here is, let me just connect to a SQLDB instance I have. So now I'm in the logical server, right? And I can query sys.databases and see which databases I happen to have here. There we go. But these databases aren't necessarily on the same node that this master DB or this list of databases is. They could be on any set of nodes around the data center or the region that I picked. So if I want to go and create a database, I just do this, right? And this is really the big deal in SQLDB. I just created a database that has 3 replicas, 3 copies of the data available in 3 different fault zones in the data center, meaning 3 different racks, essentially, right? And that's all I had to do. There's no configuration on top of that. And if I want another one, I just go and create that one. So that's really the big deal here. Anything outside of the database, you don't have to worry about. We take care of that. But anything inside, you still have to worry about, which is why we say it's about developers, right? So you still have to build a good app, right, that uses the database efficiently. You still have to worry about things like indexing and writing good queries and using the right data types and all of those things. So this is what we have today, right? We have SQLDB, which we have web and business editions, which support up to 150 gigabytes of database size. Announced that we are supporting now in preview up to 500 gigabytes in this new edition that we launched. The preview of the edition launched last year, which is called Premium. So in premium databases, you can have up to a database size of 500 gigabytes. There's also a big difference between web and business and premium. So in web and business, you pay per storage, right? A 1 gig database is lower cost than a 2 gig database, which is lower cost than a 10 gig database. But there is nothing in the price related to performance. So performance can be stochastic. It depends on what's going on in the machine or the set of machines that you're on right now, the performance that you actually get. And that's the difference in premium, where you select a premium service tier based on the performance needs that you have. So in premium, you don't pay for the size anymore. 500 gigabytes is included. So it's the same size cost for a premium database, independent of if it's 1 gig or 500 gigs. It's the performance that you're after. So just to show you, we have this Tobias 2 database, which is really a web edition database. So I can go down here, I just have a query, or we can go to the portal even and see it. So the new portal, we have a database blade in it. We're working on adding more information to it and more actions that you can do. So currently, the full fidelity portal is still the old portal, but we're working throughout this year to add all of the functionality to the new portal, as well as a lot of new stuff. So here you can see I have 1 premium database and these 2 web databases. So what I could do now is just alter database Tobias 2, modify, and I would like to change the edition to premium and max size to 10 gigabytes. So this is really just, I went in and set, I want different horsepower on this database. And obviously there's a billing change now. So we prorate charge per day. So this day I would be billed for a premium P1 database in this case. But this is really interesting, right? It means your app can go in and say, OK, right now I need more power on database 367. OK, alter database, up the power to this level. And once you don't need it anymore, you can go and scale down the power. And what we can see here now, if I query the service level objectives, we can see that this one is being moved into a P1. So we have P1, P2, and P3 with different performance guarantees. And it's currently pending. So at some point, it will finish this transition, and you have access to this P1. While we're moving it, it's still online. So we're actually moving it to a different part of the data center when you do this. So you can still continue to query, but you're still in the web edition until it finishes. So just touching on this business continuity stuff. So again, high availability is built in. And high availability, when we talk about that, we mean local machine failures. So within the data center, one of our machines failed, and your database happened to have a replica on it. Because of the fact that we have between 3 and 4 replicas of your database, we automatically let another replica pick up the work and continue running your database. And this is the same when you run, obviously, Premium Edition. So if you run a P1, it means you actually have 3 to 4 P1s running, so that once we fail you over, you immediately have access to the same performance as you used to have, which is an important aspect, right? So the secondary is not overloaded and potentially couldn't handle the load. Then you have, in Premium Edition, we announced the fact that we now have both support for oops recovery and disaster recovery. So oops recovery is human errors, right? So someone goes and drops a table or executes an update or a delete without the where clause, and you want to recover from that. And disaster recovery is this catastrophic regional failure. So this meteorite that's ever outstanding, lots of people worry about, hits our data center. The geo-disaster recovery option can basically let you have a replica or a set of replicas of your database in another region. So the way the local HA works is basically, once we get any modifications into the database, into the current primary, we will send it to the secondaries, and as soon as one of the secondaries accepts or acts that it got the change, we'll go back to you and say, this is all done. So this is always synchronous replication. There's nothing that you can do about that. You can never have data loss unless the data center disappears. The self-service restore. So here, we don't talk about backups. So we actually always took backups. But this is the ability for you guys to be able to go and restore a database. So today, before we launched this, a restore operation would be a support call, basically. But now you can go in and say, hey, I want to restore this database back up to 35 days. And you can select the exact point in time. So I want to go to 1 p.m., 2 minutes past 1 p.m., and we would bring the database back to that level in a new database. So restore always creates a new database. So that means that you can recover it, and you can fetch the data you're interested in, right, and move it into your active primary. Or you could go and rename the databases and say, oh, no, this is now my active primary. So let me just show very briefly what this looks like. And obviously, we allow this programmatically. Now, programmatically, we have support for a REST API as well as a PowerShell commandlet. But we don't have support for this in T-SQL. So overall, provisioning-related APIs going forward, we're focusing on the REST and PowerShell. So what we have in T-SQL today, we continue to support, of course. But anything net new, we basically go and enable through REST and PowerShell. One of the reasons is, in order for T-SQL to work, you have to be able to connect to something. You have to have a TDS connection, which means you have to have a logical server, which means the operation to create a logical server couldn't be T-SQL, right? Because you have nowhere to connect to run that. See if my portal comes up here. Ooh, maybe I should have connected this wired thing. Oh, fancy. While I get an IP and such. Oh. Is someone watching YouTube? We'll let that one run, see if I recover. So that's self-service restore. And the other thing that we mentioned was geo-replication. So geo-replication is now asynchronous replication. So it's very similar to what we do locally, and it's always built in. This create database was always local HA. Here you go and tell us, no, I also want this geo disaster recovery option. And that's an asynchronous replication always. So asynchronous replication means if this disaster hits, you can have a data loss, right? We don't wait for the secondary to say, OK, I got your data before we basically tell you that we finished the operation. And you can create up to 4 of these replicas. So you can have a primary, you create up to 4 replicas, and these are all readable. So you can use these to offload things like reports, queries, anything read-only you can run on those replicas. And you can also go and stop those replicas. So you can say, no, OK, this one, I want to run a test, for example. I want to test our deployment. And you can stop one of these replicas, run that, because then it becomes fully read-write database. You can run your tests and so on, and now do this very, very quickly, because that database was already caught up to your production workload. By the way, if you have any questions, please just ask them immediately, because if you ask them at the end, I'll be highly confused and won't remember what we were talking about. So, and same here, that's all available through REST APIs. And we have a bunch of APIs also inside the master database where you can ask, what is the status of my GeoDR copy? So, for example, there you can see how far behind is it right now. Might be fully caught up, or it's behind by X amount of time. And we see this by the replication stream, right? And you can also go in there and say, no, I want to stop the replica. You can also run a stored procedure to say, hey, tell me, basically return, once the database is fully up to speed. So that helps you, if you did a big operation and you want to know when is the database fully up to speed, so I can basically force a split of the replication and start playing with that other database. You also don't have to use this across regions, right? It works absolutely within the same region. You don't get the geo disaster recovery, but you can use it for, if you're not worried about that, you can still use it for reporting and so on in the same region. It has to be on a different logical server, though, because the database automatically gets the same name. So you create a new logical server, you set up the geo replication, and now you have that running. Ooh, question. I forgot there is a rule. No hard questions. So that kind of borderlines on the hard question. How not to be fired. So it sounds like a good idea. Oh, and compliance is important to us. So now, no more laughing, because they might watch this. I think we record. And so as I said, I have no idea. OK, so just wanted to cover that to make sure that you guys know a little bit more details around what Scott mentioned yesterday, I guess. So moving on to some development best practices. And here, this is kind of carpet bombing a bunch of stuff. But some things are important, and it's good to know about. For starters, and I covered this a little bit, but why SQL database is different from a programmability aspect is this fact that in SQL Server, you have all of these dependencies, right, outside of the database. You have logins, you have agent jobs, you have these TempDB collation issues. There's lots of things going on, right? And in SQL Server, when you go and move a database to another instance, you better make sure that you reconnect these things, right? And this is really the fundamental issue behind why we choose to virtualize a database rather than an instance, right? So that you don't have to think about this in SQLDB. And this is generally a good thing to think about when you develop apps on SQL Server as well. So try to focus on your app should be well contained within the database, right? Because it makes it a lot easier to manage the database, even on SQL Server if you want to do things like HA, disaster recovery, backup restore, all of these things. So that's a general good thing. The more of these links you have outside, if you're thinking about moving to SQLDB, the more work you'll need to do to handle those in the app tier instead. The next thing I wanted to cover here is basically performance troubleshooting. So how many of you guys do a lot of basically indexes, optimized queries, and so on in SQL Server? OK, a third or so. So these skills are still super important in SQLDB, right? In the cloud overall, because of the fact that you have a limit to how far you can scale up, you obviously want your code to be as efficient as possible. It's also very clear what the cost is to an app, what the cost to run an app is when you run it in the cloud versus when you run it on-prem. So on-prem, the standard generally is a new app gets a new server, and you have the option between server A, B, C, D, or so on, right? And then the app gets its own server, and for most apps, they live kind of happily there. But that's not the case here, right? Here you see very, very clearly each month what you pay to run this app. So wanting to be efficient is basically critical if you want to make sure that you have as low of a bill as possible. So we still allow you to kind of kill performance issues by upgrade to a P3, our biggest premium database. And the price for that database in preview is around $4,000 a month, right? Because it's a huge one, and we have 3 to 4 replicas. All of them are guaranteed, right? So while that might be an option, it's probably good to go and make sure that your app runs as efficiently as possible before you go down that route. And the other thing that we'll cover also is this need to be able to scale out. Because as you saw, it's very easy for me to just create more and more databases. And then I may not need to use the highest tiers for the performance, basically. So while we don't have Profiler or X events enabled in SQLDB right now, we do have a bunch of DMVs, dynamic management views, that you can basically query to understand what's going on in the database. So let me just show this. The internet thing is not very good here, so I'll go and use my local instance instead. So here we basically have some cooked query that goes against DMXEC query stats. So this is basically looking at everything that's in the procedure cache, so our local plan cache. And we track what's going on in this cache. So every time you run a query and we find it in the cache, or we put it in the cache, we'll also cache the metrics to say how much CPU time did you use to run this query? How many reads did you do to run the query? And because of that, you can use just queries against this DMV to understand where should you go optimize. So just as this example, I'm just querying this. I'm using this dynamic management function to just grab the SQL text. And I'm ordering by total worker time descending. So total worker time is CPU time. There we go. So now we can see here, this was the statement that was executed. This is at the statement level. If you have a batch with many statements, you'll get 1 row per statement here. And we can see the total CPU time that was used and the total elapsed time. Here's an interesting thing that you can look at. If elapsed time is way longer than CPU time, it means we were waiting for something, right? And we have another DMV that's in the deck, which is this exec requests, where you can see what requests are currently waiting for. So if you're waiting for something, it could be I/O, right? You're waiting to read something from disk. It's very, very common that you're waiting for your own locks, right? So someone may have an open transaction, they updated a row, and you're waiting to read that row, or update that row. So if there's a big discrepancy here, that's interesting. And we have here the calculated percentage as well. You can also, because of the fact that we have execution count in here, you can also see how frequently is this run. So if this is run, once, maybe it's not the most important thing. If it's run all the time, that's probably more interesting. And then obviously you can use the execution count, so divide total worker time by that. That will give you the average CPU time. So total is total across all of the executions. So X events also sounds like a very good idea to add to SQLDB, but while it's not there, you should definitely use this query to figure out what is the most interesting thing to go optimize. Right? And I have links at the end of the deck to some white papers where we have these queries posted. So once you have a query that you want to optimize, I want to just very quickly run through kind of what you do when you go through this. And I know a bunch of you guys already know this, so just bear with me. But the DMV query, that's to find the offender, right? The guy that's costing you the most money, essentially. And then once you have that, you go through a simple thing where you just execute the query, you ask the server to give you statistics about the query, you look at the execution plan, you see what you can do. And let me just show you an example of kind of how much you can change just by adding the right index, essentially. And this works exactly the same on SQLDB, even if I happen to run it locally now. So I have this sales.order detail table. And let's just say that what we want to do is get sales per product, right? So I want to sum order quantity times unit price, group by product ID. And we want to do this for each special offer ID. So now this database isn't very big, but again, everything counts. So if you run an app that's highly efficient, it fires off lots of these queries. Even if the query takes a second or milliseconds, you can make a huge dent in the performance by lowering that, right? So it's not necessarily that it takes 10 seconds or a minute or an hour to execute. That makes it interesting. So first of all, I'll turn on stat statistics IO on. We also have set statistics time, so you can see the exact CPU time. The interesting thing with I/O is it's a very good indicator of how much work you need to do in a database. The more data pages I need to touch, the more work I'm doing, right? So I'll turn that on, and I'll turn on the execution plan. So just running this, we apparently read the whole table, 1,237 pages times 8 kilobytes, which is, again, not very much, right? And we also apparently have a work table, so we had to save the data somewhere in order to do some more processing. If we look at the execution plan, we see a very interesting thing here. We have a suggestion to go and create an index to fix this query. So when you execute a query, the query optimizer will say, what would be the perfect index? What would my wish list look like? And then it will actually tell you in the execution plan, this is my, if you want to make me really happy someday, this is the one. Now, the problem, obviously, each index you go and create is basically another table, right, with a balanced tree structure on top of it. So you're eating up storage as well as memory when you go and create lots and lots of them. So there is some balance here that needs to be struck. So I can just go and right-click and say, well, please give me this query. Missing index details. Thank you. And it apparently, I suggest I create an index called Tobias on the special offer ID column and go and include these columns into it. Let me just do this first without including the columns, just to let you know what's happening. So what happened now is I created another table, right, which contains 2 columns, special offer ID, which we sort on special offer ID. We create this balanced tree structure. And we have a pointer from that table, that index, back to the main table, right? When I rerun the query now, you'll see that we still got 1,237 pages. And when we look in the execution plan, nothing actually happened. It didn't use the index. Why? Well, the query optimizer came to the conclusion that it wouldn't be efficient to use the index. And in this case, it's because what we would have to do is, if you just imagine just a book, right, with the index at the end. If I need to look up two things in the book based on the index, I go to the index, get the first one, just look it up, go back to the index, second one is over here. But at some point, right, these lookups become expensive, and at some point it's going to be faster for you to just read the entire book, right? So that's what the optimizer concluded here. It's faster to just read the whole book. But let's go and force it to use the index. So we'll just say with index Tobias. And then you can see we did 116,000 reads instead. So clearly the query optimizer was right. Now we do this based on heuristics, so it's not always perfect. What this included columns do is it just says, well, since I know you're going to use these columns, let's just put them in that index table so you don't need to look them up. And again, if you add too many of them, it's basically costing you storage. If you have a very read-intensive database, that might be absolutely fine, right? So with drop existing, and we'll remove the hint. And now we're down to 463. So that's way better, right? We did an index seek, and apparently this special offer ID isn't very selective. It's roughly 1/3 of the table, it seems like. What more can we do? Well, we still have this hash match thing going on over here. So that's the group by, right? And that basically means read the whole thing into memory, spill it out to disk if we need to, if it's too much, right? And basically create a hash table in memory so that we group using these hash buckets. What I could do, just to take it to the next level, I could say, well, let's add product ID in here and remove it from here. Because that means now, first we filter, right? Once we hit special offer ID 1, it's already grouped, right? It's already sorted on product ID. And now you see that the hash match disappeared. This number of pages will still be the same, right? But we didn't need to do all of the CPU, use all of the CPU power to basically create this hash table. So this is just showing you that what you can do when you look at the execution plan and just think about what the database actually needs to do, right? And you can make even simple queries way, way more efficient with spending some time on this. And again, in the cloud, that goes a long way, right, to reducing bills and making your app more efficient. OK. Connection reliability. So this is another thing that's somewhat different in the cloud, given the fact that in the Azure data centers, as well as other cloud providers, you don't buy enterprise-grade hardware, right? Don't buy enterprise-grade switches and so on. You run this commodity hardware. And that means that any machine could fail at any time, and your app needs to be resilient to this. So when you look at SQLDB, that one is different because of the fact that we do state. So all of these things that I have here, like the user obviously is unreliable, or the client application, web server, all of these things, including the database server, is unreliable. They may go down at any point in time, right? And recover quickly. But the database is durable. So once you write something to it and commit, we don't lose your data, right? Now, this means that your app probably needs to have some sort of retry logic, right? And we ship some libraries that help you do that. But retrying, there's some extra things to think about with regards to a database when you want to retry. So let's say that I have this web server that tries to do something, tries to send something to the database, a database command, right? What could happen is the link to the database, the message never reached the database engine, right? If it didn't reach the database, right, it's fine to retry independently of if you're reading or writing, right, because nothing happened on the database side. If, however, it's the fact that you didn't get the response back that happened, then it's not safe to retry if you're writing, right? Because this could already have been committed. So the problem, obviously, is you as the developer or user, you don't know which one happened, right? I don't know if it didn't make it there or didn't come back. So it's important when you do write transactions specifically to think about how can you make sure that this, for example, an insert is a good example, right? If I issue the insert, how do I make sure that I don't get duplicates when I go and retry? So there is a simple protocol that you can enable, and it's all about making each operation, each write operation, idempotent, right? And idempotent just means if I run it twice or 3 times or 10 times, it still looks the same after I ran it, right? So the key here is that you assign some sort of unique ID to the request. So I generate a GUID on the client side, right? I send the request to the server. The server keeps track of these GUIDs. You could just have a request table or something. You put the GUID there. You start a new transaction. If the request already exists, that means this already happened, right? So then you return an error, or you just return, OK, it's already done. Please go away, right? And then you begin if it didn't exist, you begin a transaction. You save this request ID within your transaction. Right? You do whatever it is that you need to do. You commit, and you return the results. Right? So now the client knows that it's safe to retry, even if it's a write operation. Because if this request ID is already there, it shouldn't redo. Right? What the client then does is, you can do this, or you do some sort of retention cleanup. But the client then sends and says, OK, I'm done. I got the response back from you. Please delete the request, because I will not try again. Right? Now this is actually fairly, as you can see, it's fairly simple to implement. And it's only important when you have these types of writes that are not idempotent, that you need to make idempotent, and that it's a problem if they happen again. Right? So you also obviously need to add some sort of retention cleanup if the client doesn't come back and say, I'm done. Right? So you don't have lots of these request IDs hanging around. How many here used Service Broker in SQL Server? No, a couple of brave, good, smart souls. It's actually very good. But it uses this protocol, right? So we have end conversation in Service Broker. You say, I'm done, right? If you don't end the conversation, you will have a lot of conversations. As we had some customer that had, I don't know, like 2 billion conversations hanging around. So this retention cleanup is a good idea. So what you should think about with regards to these retries is, with reads, you can just re-execute, right? With writes, you go and use this protocol. And then you should also keep in mind if the operation is low or high cost, right? So low cost is something that, it comes back in a couple of milliseconds, right, or second or whatever. It's probably safe to retry fairly quickly, right? But some operations are high cost, and then you can cause basically flooding on the server side, right? Because your other request, something happened with the network, your other request is still running, you come in and say, oh, I want to run this again, which can be problematic. So that's definitely worth thinking about if you have more costly operations. So for example, you could use that same write protocol for the costly read operations so that you don't go and attack the server. The other thing that's important, and this is also, again, this all applies to SQL Server as well, is reducing round trips. Right? So network chatting is, unnecessary network chatting is no good. Especially in the cloud, right? Because it's more costly there. So one thing that's interesting is try to get all at once. So if you have to get a couple of result sets from the server, you could either issue separate selects, or you could try to get them all at once somehow. So let's just say, as an example, I want to get customers and their orders, right? So one thing I could do is I have separate selects, right, where I get the customer and the order, or I do some sort of join, right, and get them into one result set. And let's just say we wanted the customer ID and order date to make it simple. Sales order, sorry, header, there we go. SO, there we go. So this is kind of obvious, right? There is a problem here, which is the fact that if I order by customer ID, I sometimes get 2 rows or more for a customer, right? Because they just had more than one order. And then you obviously have to parse this on the client side. And that can be, work, right? And it can be somewhat easy to get interesting bugs out of it. What you can do also is return this as XML. So how many in here have used 4XML? Oh, okay, 1/3 also. Good. So let's just take a look at this quickly. So what this basically lets you do is to say, hey, I want each of the rows in this select to become an XML element. And obviously, you could take the XML and just very simply convert it to JSON if you wanted to on the client side. So we'll just say, OK, these should be called customer. And they should have a customer's root element. And this is the ID. So the fact that I have the @ sign in front of this is because of we use just XPath nomenclature. So @ means it's an attribute, and no @ means it becomes an element. So this XML now becomes this. The interesting thing is with 4XML path, it's very powerful. I can go and just add any number of branches into this. So let's just say I want to add the orders. I go to sales order header and get the order date. And let's just call that one date. So there I got the orders, and then I'll just say here also, for XML path, hey, for each order, just generate an order element and return this as an XML type. There we go. So this is a correlated subquery, right? I got all of the orders for this particular customer that I'm in right now. SO, there we go. And, the from. This conference has been too awesome, so I'm somewhat tired today. Yep. Yeah. There's nothing. Well, subqueries is basically the same as a join, right? So there's nothing specific to the subquery. Now we do some, if you get a really huge XML branch in there, it's more costly than to just return it as a big table, because we basically generate a blob there with the XML that then gets that's sent over the wire. So yeah, you're right. If it's very, very huge branches, which it typically isn't, then it can be faster to generate this huge table. And here we see a bunch of customers without orders, and there we have one with 2 orders and one with more, right? So the nice thing now is on the client side, it's very, very easy to read this because the result set is already hierarchical. The other thing is batch updates. So if I want to write, right, either I send one insert at a time or one update at a time, or I try to somehow update multiple rows at any given time. And we have a bunch of different ways of doing this. And it's way more efficient, typically, to send the server a bunch of updates over one round trip or few round trips, rather than one round trip per update or insert or whatever it is you're doing. And we have a bunch of different ways of doing this. So one is round trip per execution. The other one is delimited list, right? You send some comma-separated thing, and on the server side, you have to go and basically parse that and put it into a temp table or something like that. The nice thing with the delimited list is obviously that it's very easy to do, and the performance is not too bad. It's also something that you're kind of automatically protected from SQL injection. You can use XML, which is typically slower than doing a delimited list. And then we have something that we call table-valued parameters. And again, all of these things work nicely on SQLDB. So who in here have used table-valued parameters? OK, also 1/3. Is it the same third every time? Should be interesting. So let me just I have some just pre-canned thing to just let you know what this is. So let's just look at the SQL side first. So I have a table here called test products. And then I create a type. That's a table type. And that basically tells us the structure that you're going to send this set of data over the wire to us in. So what you'll have to do on the client side is create a structure that has the same shape. We don't care about the column names, but you'll have to send us the same number of columns, same order of the columns, compatible data types, and these things. And then we can basically read this off the wire, put it in a temp table or a table variable, and then start executing on the server side. So the nice thing is now I have a stored procedure. You don't have to use stored procedures to do this. You can send them also in ad hoc batches. So I have this stored procedure, takes this values parameter, and the type is this products table type. And notice that I have to specify read only. And that is because of the fact that all other places in T-SQL will always make a copy of the data. We pass everything by value. But it would be very, very costly to keep that same behavior with tables. So because of the fact that we say it's read-only, we can just pass references to the same table around if you pass it to sub-procedures and so on. And the only thing I need to do here is just, OK, insert into test products, select from values. So it becomes very, very nice to use on the SQL side. So let's just look at, there's two different ways that you can use this from .NET. We also support it from ODBC and JDBC and these things. So the easiest way is to pass a data table. So here, what I'm doing is I'm reading just from a text file, shoving everything in the text file into a data table, and then I'm passing the data table. But just to show you what it looks like. So create a normal data table, read from the file. As long as there's more to read, I get the data. I can show you this is what the file looks like, right? And then I add it to the data table. And then we go and open a connection. I'm going to run a store procedure. It's this store procedure. And then this is the special thing. So I add the parameter values, and I say it's SQL DB type structured. And then I tell it which type I'm going to use. So this is so we know on the other side, when the call comes, where do I go check for the structure so I can validate this data that is sent over TDS. And we send it very efficiently now. We just send a header, which is this is what the data looks like, right? And then we just send it in a stream. So it's way less overhead than, for example, passing XML. We say, oh, I'm going to pass the data table, open the connection, and then just go execute. Okay? The nice thing with this is it's very easy, right? You can easily make some sort of method that just converts stuff into a data table and then sends it. There's kind of two problems with it. One is this conversion. I myself am allergic to conversions, at least when I can try to avoid them, right? So one is I have to convert something that is in some format to some other format. The other thing is we don't stream the data from the client to the server. So if it's just 10 rows or small set, it doesn't really matter. But if it's a large set, you probably don't want to load it all into memory into this data table and then go send it. That's not very efficient. It's better if you can just start sending, right? So the other way you can do this, which is streaming from the client to the server, it's not streaming on the server. So the server will always wait until the last row is received until it starts executing the batch, right? Because it needs the whole batch. So in this case, I open my connection. Same thing, I'm going to use this store procedure. Same thing with the type, right? But then, what I do is I say the value is going to be a type that implements an interface. And then I go and execute. The interesting thing with this interface, it's just IEnumerable of SQL data record. So I implement this interface. And what I do in here is I take that stream reader in, apparently, and the enumerator create a data record, a single data record, right? Read a line from the file, split out the columns, I set the values in that record, and then do yield return. So this means now this runs, and with a single data record each time, I reuse their data record, right? Whenever the buffer in ADO.NET fills up, ADO.NET will go and send it over the network, right? So now I will still load stuff into memory, but it depends on whatever the network buffer is, and I don't have to go implement it. So this now is way more streaming, right? I can take a 1 gigabyte file and start streaming it over. I'll need 1 gigabyte on the server side, but I won't use a gigabyte on the client side. So just to show you, here, streaming TPP. So I get here. Sorry, I should have put the breakpoint in here. So I get here, and once I start executing, then the enumerator will be used, right? So I keep sending the values, keep sending the values. And after a while, it's done, right? And I have all of the values on the server side. So you can do the easy way with the data table, which is very simple, easy to use. It's not that hard to obviously implement this interface, and then you can stream the data to the server. And you can get a tremendous performance boost, especially if you send larger amounts of data. If you send very few rows, it might be faster to just build a big string and run it. There's some articles out there on what is the most performant way. Cool. So the last thing I wanted to touch on is this charting business. So partitioning your data across databases. Did you have a question? Just before, it's easy or hard? Okay. Oh, okay, okay. Then fine. Yep. No. EF does not support TVPs right now. Sorry. Any other questions? I don't actually know. But I'm happy, well, not super happy, but I can take your, I can give you my card, and then we can get the right people to have a look at that. Okay. So this is more kind of on the design aspect, specifically on SQLDB. So our largest installations, probably by far, is basically ISVs or SaaS providers, software as a service providers, that run their business on SQLDB. And traditionally, an ISV would go and create, most often like this, right? Each customer has an app, and they have a database. Sometimes they have more than one database, right? And it turns out this pattern scales works very, very nicely in SQLDB as well. So what we see happening there is, and see working very well, is basically that the ISV or SaaS provider creates a database per customer. You can also obviously put multiple customers in one database. Some people do this based on their customers' tiers, right? So if I have a kind of high tier customer, might be super useful for me to put them in their own database. That means I can control the performance that database has. I could do restore, for example, just for that database. I can allow the customer maybe to connect with Excel or whatever directly to the database, right? For customers that are basically lower priced, I may want to put multiple customers into the same database to just get the cost as low down as possible. And then you obviously have to go through the work yourselves to make sure that customers can't see the data, other customers' data, when they're co-hosted in the same database. Either you put them all in one table, or in the same tables, or maybe you separate them by schemas, or something like this. So, if you look at this typical, I think this is Northwind database schema, but typical OLTP schema, if you want to go and chart it, what you need to go and do is exactly like if you did distributed partition views in SQL Server, for example, or any partitioning scheme. You need to decide on what you partition on, and that's this mega key decision, right? And then you have to put that partitioning key in each of the tables, right? So the kind of common simple example is I partition on customer. So each of my tables, I would add the customer ID column to. So then you could do something like this, right, where you could both support logically have different customers in different tables within one database as well as in other databases. And then if you do this thing within one database, it's probably important for you to go and develop code that can move customers between databases so that you can give them their own database or do some sort of load balancing. One thing to note there, their TVPs are very, very useful for that code, right? Because you could use the TVPs to transport the data between the databases programmatically in a nice way. You could also use the bulk copy APIs. One big thing to think about here is that there is no cross-database queries in SQLDB, right? So if you want to go and summarize data across databases, that would be a costly operation that you have to go and implement yourselves, right now at least. So your design should try to be focused so that you minimize the need for doing cross-database queries. So you may want to do, for example, in this example, you do maybe cross-database queries to find out the patterns of usage of your customers, or how big are the orders tables, how are they distributed across databases and so on, in order to maybe do some reshuffling of the data. But individual customer queries here would not span databases, right? As long as they don't span databases, you don't need to worry about it. Yep?
If you use sharding, you have from the application level a single connection string to one database, and then inside of stored procedure, you check which shard you should carry, or how do you work?
Yes, we have a good question. So we have a slide on this. That's here. So the question is basically, what about how do I know where to connect? So you need to store a directory of your, basically the topology of your customers somewhere. And that directory becomes very important. So many of our customers using this actually use premium databases today for their directory, right? Because the directory, they have much higher requirements on than maybe individual customer databases. The other thing that's very important with the directory is to be smart about how you cache, right? Because you don't want every single query to hit the directory to ask, okay, what's the connection string to, which logical server, which database is this particular customer on? So what you probably want to do is you cache this, you keep a hash table of where should I go on the web server. Once you connect, you somehow enter into the query when you connect so that the database that you connect to can invalidate the cache. right? So when you actually run the query, that database will tell you, ooh, I'm not the right place, right? So there's actually two maps in question, right? One map is the directory across databases, and each database also needs to know which customers or whatever, right, am I the primary for, right? So once you hit and execute the query, that database would say, no, 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 I'm actually not the right place here. And then you know to invalidate the cache and go and just refresh it. And if you do it this way and spend some time thinking about the design, you can have a very, very elegant and extremely, extremely scalable solution. So we have customers that have thousands and thousands or tens of thousands of databases that do this today. And the interesting thing from your side of the story, right, is it's all developer work. Right? It's all thinking about how do I do this in a smart way, right? How do I write the app in a smart way? You don't have to worry at all about the management aspect, right? Having 10,000 databases, it's not different from having 2 databases in SQLDB, right? Except for the price. We'll charge you more for 10,000 than 2. So finally, the thing that you probably want to look at is kind of the cost signature, right? So when does it make sense to start shoving more customers into a single database versus giving them their own database, right? And that very much depends on how you sell your own application, right? How your own application is built. We also have lots of non-SaaS vendors that do these patterns where maybe it's just users, right? And it might be a free website, but they still use this technique to very easily scale out. The final thing I wanted to mention, since we're just on time, is the reporting queries. So if you want to go and implement queries across charts, there are some example libraries out there that could help you with this. My friend Scott here in the front also has some thoughts on this, and I think we'll have a presentation, we'll publish something in May or so with some helper libraries to do this. But basically what it amounts to is you'll have to issue the query against each database, and if you have a smart map in the directory, maybe you can do some partition elimination there and say, I actually only need to query these 3 databases, not all 10,000, right? You issue a query against each of the databases, and you basically store the results either in memory, or it could be a hugely long operation, so you may want to actually use a separate SQLDB instance or separate SQLDB database to store the intermediate results. So you can see this example here. I went to the first database, issued the query, shoved the results into my result database. Next, shove the results. And obviously here you could easily do this in parallel, right? You could fire all of these off at once, and they could all insert into the results database at once. Once you went through all of them, then you would return the result to the user, right? And because of the fact that you saved the result somewhere, you don't have to worry about losing it. And you could actually restart if something fails. And one important aspect here is this one, right? So it wouldn't be transactionally consistent, right? You won't, sorry. So it wouldn't be transactionally consistent. Some of the results will be from 1 p.m., some from, 1 minute after 1 p.m., some maybe from 2 p.m., depending on how long the operation goes for. And that's something that you have to basically live with. Otherwise, you would have to architect your tables in such a way so that you could write temporal queries. I have a couple of links here to some white papers that might be interesting to read, both about performance in SQLDB, the top ones are, and the last one is about performance in SQL Server on VMs. If you're interested in that. Otherwise, I'll stay up here, answer questions, easy ones, and I hope it was interesting, and thank you.